In the previous video, we discussed different methods of numerical integration. These were methods of approximating the area under a curve between the curve and the x-axis for those functions where we're unable to come up with an antiderivative function. So we're not able to use the fundamental theorem of calculus. Now, of course, most functions don't have antiderivatives. We spend most of our time in calculus studying those that do. But there are a huge, vast number of functions which don't have antiderivatives, or for which, even if they exist, we cannot write them down in terms of elementary functions. And so instead, we have these methods of numerical integration that we discussed in the previous video. These would be the methods of the left Riemann sum, right Riemann sum, midpoint Riemann sum, the trapezoidal rule, and Simpson's rule. In this particular video, we're going to take a closer look at the trapezoidal rule and Simpson's rule, but using a Python program. Now, I do not assume that my students have ever done any programming and that they don't know Python. I have a series of videos that explain how to get a free CoCalc account and how to set up what's called a Jupyter notebook in CoCalc so that they can run a Python program using Python 3 as the kernel. What we're going to do in this lab is we're going to go through and briefly review what the trapezoidal rule is and what Simpson's rule is. And then I'm going to go through and give an overview of what the program is doing. Now, why is this useful? A couple reasons. One, as you become an engineer or a mathematician, you need to start learning how to program a computer in order to solve certain kinds of application problems. This is where mathematics is really starting to grow and be used more often in the world today. So this is an important skill to have. By giving you the program already, I let you experiment with actually solving problems using a Python program, but without having to come up with the code on your own. So it's sort of an introduction to programming by using an already written code. Now, you will have to change the functions in order to complete this lab, but everything is already written down for you. It's a simple matter of understanding what the code is doing and understanding the formulas for the trapezoidal rule and Simpson's rule, so you know which pieces of the code will need to be changed for a different function and a different interval of integration. The lower limit of integration and the upper limit of integration. Let's go ahead and get started now. Let me share my screen with you. And that way you can see the code more easily. Now what we're going to do is we're going to start again with a brief review of what the trapezoidal rule is. Again, I allow my students to use the free online system called CoCalc. Free account is plenty powerful enough to run this very small program, but for a very nominal fee, you can get one level up, which makes it program even faster. But we're talking about the difference between maybe 2 seconds and 4 seconds, which really isn't that long. So I think you'll find that the free is more than powerful enough for what you need. We want to again find the value of a definite integral. So we have the integral from a to b of f of x dx, which using the fundamental theorem of calculus would be the antiderivative function evaluated at the upper limit minus the antiderivative function evaluated at the lower limit. But this supposes, of course, that we can come up with the antiderivative function, and there are many functions for which this is not possible. For example, e to the x squared is one such function. It has no known antiderivative. It's known as the error function. And because it comes up so often in applications, we've given it a name and a way of writing it down, ERF of x. And we need some way of approximating the definite integral of such a function, even though we can't write down the antiderivative function. So we're going to start now. And we're going to use this function here, x cubed over e to the x, as our integrand, as our test function. And we're going to integrate between 0 and 8. Now we're going to do one for which we actually are able to compute, and so that we know what the actual true answer is. And we're going to use that in order to estimate how accurate the trapezoidal rule and Simpson's rule are. But again, the real purpose of these is to work on functions for which there's no known antiderivative. Some things to remember as you're working through the lab: don't use tab when you're writing in Python. Instead, you want to use 4 spaces. 4 spaces is a tab. Why not 5? I don't know, but there's 4. You may have to delete any tabs that you see and replace them with a set of 4 spacings. In general, in this particular lab, the directions are given with a black background and white lettering, and the code follows it. So let's start with the initial coding for the lab, and you'll see that right here. The first thing we're going to do is give your name and the name of the lab in triple quotes. Now, one thing about Python is Python will not accept curved apostrophes or quotes. And by curved, I mean curved. So unfortunately, if you type something in a Word document, it automatically corrects them and makes them curved. And you have to undo it to get them back to straight. Yeah, I'm talking about straight and curved. So if you type it directly into the CoCalc system, directly into a Jupyter notebook, they'll automatically come up straight. If we use a set of 3 straight quote marks at the beginning and 3 straight quote marks at the end, it interprets everything between those sets of quote marks as a comment, and it ignores it. It does not consider it to be executable code. So this just says, put your name in first and identify the lab, enter the next 3 lines in one input line, then hold the shift key while hitting enter, include the quote marks. Now, in order to get it to execute a line, there are boxes for each individual input space, and we'll see what they look like in a second. So when we talk about a line, we're not talking about one row of letters. We're talking about one box. One box is one line. In order to get the program to execute, we hold down the shift key and hit enter. This is my name, which is right here, Johanna Debrecht, Trapezoidal Rule and Simpson's Rule, methods of approximating area. So this is here in quotes. Now we're going to set the value for the exact area. And this is something I've already computed using other techniques. You don't need to worry about where it came from. But this value, 5.7457, etc., is an approximation of the exact value of the area under the curve of our test function, which we see here, between 0 and 8. And we're going to use that in order to estimate how accurate trapezoidal rule and Simpson's rule are. Now, we will need to convert this exact value into a floating point decimal number, and we'll call it exact so that we know it's the exact value. So you'll note that each of these lines that's explaining what we're doing is actually in quote marks, meaning that they're comments, so it ignores it. It will print it, but it ignores it and doesn't consider it executable code. This line here where it says exact equals float and gives the digits inside parentheses is the first line of executable code because there are no quote marks around it. What we're doing is we're setting the value of a variable called exact to be that number. So it's not really a variable, it's more of a constant. So exact is set to be this number where it's a decimal number, which is what we indicate by saying float. Now, how can we test to be sure that it entered it correctly and that it stored this number in the location called exact? You can test this by just entering into another line exact. So you just write exact without quote marks around it, and then you can hold down the shift key and hit enter. Now, all of this was typed into one line or one box in the CoCalc system, or you could have put it in numerous boxes. Here's what the output looks like, and you can see that I put mine in a couple of different boxes here. So you can see I put my name and the title of this lab in triple quotes in the first input box or the first line of code. It's an input line, which you can see it says N. And when I execute it, it simply puts out that output and it ignores everything inside of it and considers it to be a comment. The next input line, I put exact equals float. You'll notice that it's color coding different things. It tries to help you out by color coding the parentheses so you know which one goes with which one. And then you can test it by entering exact into one line by itself, holding down the shift key and hitting enter, and then it will give you back this exact value. So you know that it has stored that value inside of exact. Now let's review for just a moment what the trapezoidal rule does. Again, the trapezoidal rule is approximating the area under a curve. So let's go out here to Desmos and let's take a look again at the function we looked at in the previous video, which is xe to the negative 1/2 x. And when you're looking at this, you're trying to approximate the area under the curve between the curve and the x-axis. Instead of using rectangles with flat horizontal tops, we're using trapezoids. Remember, trapezoids have exactly 2 parallel sides and 2 sides that are not parallel. So we take the endpoints where it intersects the function and we connect those 2 points with a straight line. And then we use the formula for the area of a trapezoid, which is the average of the 2 parallel sides, 1/2 base 1 plus base 2, multiplied by the height, the perpendicular height of the trapezoid, which would be the perpendicular distance between the parallel sides, which in our case is this distance here along the x-axis. This is our delta x, which we find by taking b minus a and dividing by the number of boxes. So in this case, it's 6 minus 1 divided by 1, 2, 3, 4, divided by 4. And that indicates how wide each individual subinterval is. So we can compute the area of one trapezoid. Notice that the points between the first and the last get used twice. Once as the right endpoint of the box on the left, and once as the left endpoint of the trapezoid on the right. So the ones in the middle get used 2 times, whereas the one on the far left and one on the far right only get used 1 time. And this leads to the following formula, which we saw in the previous video. Again, the width of each subinterval is delta x is b minus a over n. And the formula for the trapezoidal rule for n trapezoids is 1/2 delta x, function value at the far left endpoint, plus double the function values at each of the interim endpoints, plus f of x sub n, which is the function value at the far right at b. Now, the precise area under the curve, of course, would be found by using the definite integral, which is the limit of the Riemann sum, as the number of trapezoids goes to infinity. Now, supposing, of course, that you can't come up with an antiderivative function, we can still use this formula with as many different trapezoids as we want to approximate the area under the curve. And that's basically what we're going to do in this lab. Here are some different examples of the trapezoidal rule applied on different functions. And you can see that the tops are connecting with a straight line segment between the endpoints of each subinterval. It is going to approximate the area under the curve. The more boxes you take, the better the approximation will be. You can see that when the part of the curve is more or less linear, it's a very good approximation. And where there's more curvature, it's less good of an approximation. It's not as close. Let's now talk about how to set up the program in Python. First, we need to import some libraries so that Python can do what we need it to do. These are sort of some standard libraries that most programs are going to import. So what we want to do is we want to import NumPy as NP. NumPy stands for the Numeric Python Library. So this is where it calculates things as numbers as opposed to as symbols. So there's a SymPy and a NumPy. SymPy interprets things symbolically, and NumPy interprets things in terms of just numbers. We also want to import from matplotlib, import pyplot as PLT. Now, what does this mean? Matplotlib is the mathematical plotting library. So it's a whole list of different commands for plotting. And we want to import pyplot with Python plotting program, which itself has many different commands. So this is like a huge library. This is like one floor of the library. And we don't want to have to type PYPLOT every time because we're super lazy. So we rename it as PLT. So PLT is our abbreviation for pyplot, which will give us all the commands that we need in order to graph these. Because we not only want to approximate the area under the curve, we want to see what we're doing so that we really make that connection between the numerical integration, the computational mathematics we're doing, and the image, the actual graph. We want to connect these two concepts. So we're going to be importing these two things. This first line gives us the plotting ability. The second one gives us the ability to evaluate functions in terms of numbers. And again, why import NumPy as NP? Because we're too lazy to type NumPy every time. NP is less typing. Mathematicians are notoriously lazy, or as we would say, we are super efficient. If there's a more efficient way of doing it, that's the way we're going to do it. Now, here is what the code looks like when you input these lines, hold down the Shift key and hit Enter. You'll notice there's no output from either one. These do not produce output unless you actually use them and tell it to print the output, but it is still calling them up. So it's calling them up and saying, hey, get ready. I'm going to use you later to plot, and I'm going to use you later to evaluate some functions in terms of numbers. So, for example, e to the x becomes np.exp of x, and e squared becomes np.exp with parentheses around the 2. Now, what is this doing? By putting the np at the front, we're telling it to evaluate it as a number, not a symbol. If we wanted a symbolic, we would have to use a different command. And I do that in some other labs, but not this lab. In this lab, we're mostly concerned, of course, with approximating the area under the curve. So we actually need numbers to add together. So the exponential function is written in numeric Python as np.exp with the x following it. E squared becomes np.exp parentheses 2. If we want to call it cosine, we need to tell it to approximate the cosine as a number, np.cos parentheses x. Now you can always check this by plugging in some value for which you know what the answer is. For example, I know that e to the first power is 2.71828182845.9, blah, blah, blah. So I could put in np.exp parentheses 1 and hold down the Shift key and hit Enter to check that it's giving me the right value. So let's take a look now at what that would look like if we put that in. So you'll see right here that I've executed 2 test cases. I did np.exp of 1, and you'll see that it did give me the value of the exponential number, Euler's number, the natural number. And the second one, you'll notice that I tested the value of cosine of pi, and you'll notice that pi itself is another NumPy command. So it's, or NumPy, you can call it NumPy or NumPy. So when you're looking at it, I have np.cos parentheses np.pi, pi. So pi itself is represented by a command in the NumPy library. And I know that the cosine of pi is supposed to be -1, and indeed it does return that value. So this lets me know that it did call up the routine or the library for NumPy. Now, there are lots of different ways of coding the trapezoidal rule, but one of the fastest ways and most efficient is to use what are called vectors, which are basically lists or arrays of numbers for the x and the y coordinates. So like a list of numbers, right? So we're going to use dx for delta x. That's the right endpoint minus the left endpoint divided by the number of boxes. That's delta x. That will give us the number of trapezoids. We're again going to follow the notation that we use in calculus, We're going to use A for the left endpoint of the closed interval. That will be the lower limit of integration. We're going to use B as the right endpoint of the closed interval. That would be the upper limit of integration. We'll use F as the name of the function. That's the integrand. That's the function on which the trapezoidal rule is operating. Now we're going to make our X values into a list, into an array with the command linspace. So this gets into linear algebra a little bit. Don't worry if you don't know any of that. Linspace stands for linear space, which is just a linear list of numbers. Since the X's are in an array, then the Y values are also going to be stored into an array. Remember that each indentation is 4 spaces, and here is the code that you will need to put in. This is the trapezoidal rule in Python. So remember, we're going to enter all these lines of code into one line. These are lines in Word, but they all go into the same box in the Python code. DEF stands for define. Trapezoidal. This is the name we're going to give to it. If you wanted to name it something shorter, you could name it something shorter, but I wanted to make sure to use a descriptive name for my students. So I named this function routine that I'm defining trapezoidal, and it acts on 4 different things. It acts on a function, the left endpoint, the right endpoint, and how many different trapezoids I want to take. So F is the integrand, A is the lower limit of integration, B is the upper limit of integration, and N is how many subintervals I want to divide that closed interval from A to B into. Uppercase N equal 10 is just a number that we will need in the command in order to run the routine. So we'll see where N is coming up later. You could set it to a different value, but 10 was roughly as much as I needed. And what is this doing? Well, you'll see there's a hashtag right here. And this hashtag, if it's entered in a short enough number of characters, makes whatever follows it into a comment. So it ignores that part. It views the N equal 10 as an executable command, and it considers this comment after it to be non-executable. So what we're going to do is we're going to use however many points we set, which is 10, times N plus 1 points to plot the function smoothly. When we plot it out, we need a lot of data points. So basically what I do is I take this number right here and I multiply it by the number of trapezoids and add 1, and that will plot it more smoothly. So I get a better picture. Now, I define something called result to be half of F of A and half of F of B. Notice that I'm using the asterisk for multiplication. Python does not understand mathematics. It does not understand if you put things side by side that you intend for them to be multiplied. Every multiplication must be made explicit. So you cannot put in like 2x, you need 2 asterisk x to indicate you need multiplication. So this is going to give me half of the first and half of the second. And then what is it doing? So I'm getting the front part and the last part of the trapezoidal rule, but I'm missing the middle. Remember what the middle was. The middle was double each one of those. So this is a loop, and it says for I between 1 and n, the number of subintervals, result, add to it, and let it equal. So what it's going to do is it's going to compute these, then it's going to compute this and add it onto it and set the new value to be equal to result again. So it's not going to lose this. The first time it goes through, it's going to add this on. And what does this do? Well, it takes the function value at a plus I times delta x, and it adds that onto what was already here. And it's going to do this repeatedly for I between 1 and n, and this will give us the trapezoidal rule. And then finally, we have the result times equals. What does that mean? After I've completed this part right here, I have the interior part of the trapezoidal rule. Half of the left endpoint, plus all the others in between, plus half of the last one. And then what I need to do is I need to multiply by the width of the interval, which is delta x. So it's going to take the result of all of this, multiply it by delta x, and set it to equal result. So in a sense, I'm replacing the value of result every time I go through this loop. And the last thing I do is multiply it by the width of the interval. Then it will be stored in result. Let's take a look at the next part of this program. In the next part of this program, I have x equal np len space from a to b to n plus 1. These are all the x values. Remember that I'm storing them in a list of numbers called an array, which will be in linear space. np.len space is a way of calling up a command and saying, hey, I want you to store a bunch of values for me in a list. I want you to start at A, and I want you to go to B, and I want there to be n plus 1 of them. And then I want you to have y equal to f of x. So the right x is going to be linear space A to B, uppercase n times lowercase n plus 1. So that's how far we're separating them out. And right y is going to be f of right x. So this is plotting out the points. So we have a right x and a right y. And then we're going to plot these points. So it's listing out all the ordered pairs from computing the endpoints on each subinterval. So it's going to plot right x and right y as a point, and then it's going to go through, and this basically, all of this in here is having it plot all the different points. So these are the linear arrays. So we have x1 to x1 by x of 1 plus 1. And these are going to be the way that we plot it. Now down here, this B stands for blue, edge color blue, alpha, how big it is. And we want to fill the space with color. So we're filling the space with color. And then we want to plot a title on it. You'll see that I've used the command plt fill. This fills it with color. PLT is pyplot again. Remember, that's our plotting code. And when then we plot a title, notice it's in those straight quote marks, trapezoidal rule, n equal, and then it's not going to print the curve brackets. It's going to actually say what n is, and we format this. And then we have to tell it to actually show the command, which I always think is kind of funny. If you set up all these commands for how to plot it, it won't plot it unless you tell it to show the plot. So it'll do all the work, but not show it. So the last command is plt.show with empty parentheses, and that will tell it to plot it. The last thing you want to do is you want to see the approximation for the area under the curve, which was the last value that got stored under result. So then you return result. So this is basically the code. And here's what it looks like when you put it into CoCalc. And you'll notice that defining the trapezoidal routine is at the far left, and all of this is indented underneath it. And then when we have this for loop here, it's also indented underneath that, but plot title and plot show are back indented under define. And then the last thing is return result. So this whole list of commands here is a part of the routine called trapezoidal. So this is running the trapezoidal rule on a function called f, being integrated from A to B, and we get to choose how many different subintervals or how many trapezoids we want. Now there's no visible output to this because we haven't done anything. We're just defining this routine to run, but it hasn't actually run yet. So now we need to run the trapezoidal rule on our example so we can approximate the area. Now I'm going to use the letter V, I think is what I used in here because I haven't used it for anything else. And then we want to define some constants called trap4, trap8, or trap16 to indicate what the value of the result is when I'm done computing. In other words, what's the approximation of the area under the curve using 4 trapezoids or 8 trapezoids or 16. So here's the code that you need in order to do that. Again, we'll put all of these lines of code into one rectangular box. That's one input line. Now, what is lambda t? Lambda t is a way of defining a routine or a function in a shorthand where I don't have to use the def command for define. I could use the def command, but what it does by saying lambda t is I'm saying, hey, I want to define a function very quickly. And by the way, t is the variable. Then I use a colon, and then I give the expression of the function. And I define it to be v, but without using the define command. So this is t cubed. Notice that to the power is not using the caret symbol, which is pretty common. It's a double asterisk. So a double asterisk is to the power of, divided by np.exp of t. This was our function, right? X cubed divided by e to the x. Now we use t as the variable. And again, this is just a quick way of defining a function without def. We could have done def, and that would have been fine as well. And then we set the number of boxes. In this case, n is 4. And then we set trap4 to be the result. So when it returns the result, it's going to store it under trap4. So I want to call up the function. V is the function, the integrand. Integrate from 0 to 8, use 4 different trapezoids. And then I want it to print the value of trap4. So here's what happens when we call up that routine and execute that line of code. What it does is it goes out, it makes a definition for what V is, and it defines the number of boxes to be 4, and then it calls up trapezoidal using function V from 0 to 8 using 4 different trapezoids. And then it returns the value in trap4. And you'll see the value written down here. So you can see the 4 different trapezoids in the picture. And this is what all the commands in plot were doing. It prints out the command right here. Now we can run the command again for n equal 8 and n equals 16. In fact, we can put them in the same line of code if we want to, and it will simply print them one after the other. So we set n to be 8. We again call up trapezoidal with the function v from 0 to 8. Those are the limits of integration. Now using 8 trapezoids, and set that value into trap 8 and print it out. And then we do n equals 16. And then, of course, we want to print out trap 16. We want to see what that value is. We're setting trap 16 to be the result of trapezoidal. And then the code and the output would look like the following. So here is what it looks like using 8 trapezoids. You can tell it's a better approximation. It's getting closer to the true value that we set previously called exact. And here's what it looks like when you run 16. And on 16, you can barely see the difference between the actual curve and the trapezoids, except right here where the change in curvature is most extreme. Where the change in curvature is most rapid, then we can see some white space creeping in there. And we know it's still not a perfect approximation. Now, obviously, the number of trapezoids affects the accuracy of it. So if you took 100 or 1,000, then it's going to be far more accurate. So we want to estimate the error in what we're doing. We want to get a feel for just how accurate is the trapezoidal method. So we want to compute the error. Remember that the exact value, which I gave you, is stored in something called exact. So we want to compute the error involved, and we want to print trapezoidal rule n equal 4. Error is exact hyphen trap underscore 4. So we take the exact value and we subtract trap underscore 4. So the hyphen is interpreted as subtraction. And then print trapezoidal rule n equal 8. Error is same for n equals 16. What does the code look like? Now you can see the code right here. So we can see that when we use 4 trapezoids, the error is out in the 3rd decimal place, so 6 1,000ths off. When we use 8, it's 2 1,000ths off. And when we use 16, it's about 1.7 1,000ths off, right? So we can see it's getting far more accurate. Now, if I were to run the code with 1,000, then I would probably have a string of zeros here, and it would be far more accurate. So I can get far more accurate by using more trapezoids. Now we're ready for you to try this. What you want to do is you want to repeat the process that's already been done, and you again want to approximate using 4, 8, and 16 boxes, not a whole lot of subintervals, but some. You will need the command for sign, which is np.sign. Remember to use 2 asterisks for raising something to a power, and you will want to change the name of the function. It's always good programming practice to change the name of the function, not reuse names of functions, because computers never forget. You forget you called something V, and now you're calling something else V, but the computer doesn't forget and it can get confused, or rather, the computer doesn't get confused, but you do. And you can be surprised by it not giving what you thought it was going to give because it remembers the old name or what the old function was. So we're going to use W and not V. Now we want to set the new exact value to be 1/2 minus 1/2 the cosine of 25, which is this value right here. Now, in order to do that, I named it exact W, which is for the U-try example. And so you're going to have exact W equals 1/2 or 0.5 minus 0.5 asterisk for times. Remember, you need that in there. NP dot cosine 25, which is approximately this number right here. That is the true value of the integral of x sine of x squared between 0 and 5. Now, again, I'm using functions for which we know the exact value, so we can estimate the error. But if you were doing this in the real world, you would be applying this numerical integration technique on an integrand that didn't have a known antiderivative. That's the whole point of why we use numeric integration. So let's take a look very quickly at what this particular function looks like. And you can see right here a Desmos graph. So this is what x sine of x squared looks like. And I've shaded in the region between 0 and 5. So we can see this parts both above and below the axis. And we want to estimate that area right there. You can see there's lots of changes in curvature. So it's highly likely that the trapezoidal rule will not be as accurate as Simpson's rule. Now, let's talk about Simpson's rule. So I'll leave you to do the U-try on your own. Let's now talk about Simpson's rule. That last example had lots of curvature in it, which makes the trapezoidal rule not a great choice, because the more curvature, the less accurately that slanted top of the trapezoid can approximate the curve. So it makes more sense when you have integrands with lots of change in curvature that you use a top to the subinterval that is itself curved. And that's in essence what the Simpson's rule does. Let's go ahead and review what Simpson's rule looks like. Simpson's rule assumes that you have a function that's continuous over some closed interval, and you have, or at most, you have a finite number of discontinuities of the closed interval, and you're going from A to B, and you're going to decide to divide it into n subintervals. So again, delta x is b minus a over n. Now, when we're doing Simpson's rule, we must always choose an even number of boxes, because we're going to take a pair of boxes, two subintervals side by side, and we're going to use the tops, the 3 points that intersect with the function, to calculate a curved parabola as the top of those two subintervals. So let's take a quick look out here on Desmos. And you can see right here, let's go back to the first interval, which makes a little bit more sense. So let's be looking at this one here. So again, it's dividing it into different subintervals. These are two subintervals, not one. So we have the subinterval from the red to the green dashed line, and then the subinterval from the green dashed line to the blue dashed line. And you can see where those vertical line segments intersect the function, and it gives you the far left, the far right, and the point in the middle. Those 3 points have a parabola that goes through them. Actually, they have infinitely many, but there's one obvious one. And we can use algebra to solve for that. And then we can actually, believe it or not, use algebra to compute the area under the curve of this parabola. So we're actually able to use algebra to find this without using calculus. Now, why would we want to do that? Well, because the whole point of Simpson's rule is that we have a function for which there's no known antiderivative. So we wouldn't be able to use calculus. So it's got to be able to be computed using algebra, and we can. So instead, you'll see here in orange that we have this parabola, which is being used to approximate the top of these two subintervals side by side. And then you move over to the next two and notice that you're going to reuse this point again, and then the point in the middle, and then the point down at the bottom. So notice that some of these points get used twice, and some of them get used more than that. In fact, the formula goes 1, 2, 4, or 1, 4, 2, 4, 2, 4, 2, 4, back to 1. So the far left gets used once, the far right gets used once, and in between we have this pattern of 4, 2, 4, 2, 4, 2, 4. And you can see here that they're being used again, and that's because of the algebra involved in finding the area between the parabola and the x-axis. Coming back over here, we can see the formula for Simpson's rule is 1/3 delta x, and here's our pattern, 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, back to 1 again. And that comes from algebra. If you want to see a derivation of that, MIT has a great video. It's rather old, but it's a great video explanation of how to find the parabola going through the 3 points, and then how to come up with this formula for Simpson's rule. So you can look for that on YouTube. The precise area under the curve, of course, would be given by the definite integral, but if you don't have an antiderivative function, we can use Simpson's rule to approximate instead. Now here are some images, some still images of what you're looking for here. So you have this shared point in the middle, the far left and the far right, and you're putting them all together and you're reusing them. So again, what we're doing is we're approximating the actual curve, which is pictured here in blue, with a parabolic curve, which is pictured here in red. For functions that have a lot of curvature, it sort of makes sense to use something that's curved to approximate the top of the subinterval, as opposed to using a straight line, like in the left Riemann sum, right Riemann sum midpoint, which I'll use horizontal line segments, or the trapezoidal rule, which uses a slanted line segment. And it will make a little bit more sense. So if you're looking at some of these down here, you can tell that they can become more and less accurate. The more points you have, the more accurate it's going to be. But again, you always have to take an even number of boxes, because it takes 2 subintervals to create one parabola connecting them. Now let's take a look at the code for Simpson's rule. Again, we're going to be using arrays for our x and y. We're going to still use dx for our delta x, which is still going to be b minus a divided by the number of subintervals. But this time, the subintervals have to be an even number. Now, unlike the trapezoidal rule, they have to be even for Simpson's rule. And we're going to, again, use a for the left, b for the right, f for the function, or in this case, since we've already used v and w, we might use something different. This is the code just for Simpson's rule. Now, Simpson's rule is a more complicated formula than the trapezoidal rule because the tops are parabolic. So be careful when you're inputting the code. Here's the code for Simpson's rule. Now, I'm not going to go through all of these commands. I'm just going to go through some of the basics. So this is defining the Simpson's vector. So this defines it as a vector. And we have called it up on some integrand f from the lower limit of integration a to the upper limit of integration b using an even number of boxes n. And then I didn't have a comment after this, but the hashtag is still there. You can delete that if you like. If n is 2, not equal to 1, raise the value error, n must be an even number. In other words, if you put in an odd number of boxes, it's going to raise an error that tells you n must be an even number, and then it's going to stop, right? It's also going to give you an error message if you put in something where the lower limit of integration is larger than the upper limit of integration, and it will print out incorrect bounds. A should be smaller than B, or you will get a negative area. You'll be integrating backwards. So these are two error commands just to let you know whether or not you've input it correctly. Then we define dx to be the floating decimal point number, b minus a divided by n. And we create another array of numbers listing out all the x values from a to b, n plus one of them. And then, of course, we define y to be f of x. And then we have Simpson's rule. Now, what is this doing here in the middle? This is computing basically Simpson's rule. So you'll see the left endpoint, right endpoint, and 4 times the middle. And you have dx divided by 3. Now, don't worry too much about what it's doing in here. It is computing the value of Simpson's rule. And then it returns the value as Simpsum. All right? So the notation in this last line, it can be a little bit confusing. Since we turned our x values and our y values into lists or arrays, the square bracket notation explains which numbers in the list to use. So the first number is always 0, the second is in position 1, and so on. So if you have them listed out, remember we talked about the first one as being the 0th one, and the second one as being the first one, and the third one is being the second one. In other words, instead of starting the count at 1, Python starts the count at 0. So the position -1 refers to the very last one in the list. So f of b would be in the -1 position. So what does it mean to have y square bracket 0 colon -1 to 2? It means to add all the y values, starting with the first value in the list, which is the 0th one, to the last value in the list, which is the -1. So go from the first to the last with a step of 2. So every other one, that's basically what it's doing, is it's skipping every other one. Since the coefficients go 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 1, this includes every other term once, including the f of a and f of b. And to get the multiples of 4, we need the skip term. So we start with the second number, which is in position 1, and we go every other one. So starting at 1 and going by 2. This accounts for all of that notation. Notice that the ending value was left out, so there's no number in between the colons, and that gathers all those skip terms. So this generates the list of values that we need for the y value of the approximation using Simpson's rule. Now let's see what the code looks like. So the code itself is relatively short, but it is complicated because of this command right here, which is using the arrays. And of course, this last one here started in the 3rd position and goes every other one. So this is picking up all the ones with multiples of 2, and it's giving us those values in there. All right. So now we want to produce the graph of Simpson's rule along with the approximation. This part right here does the approximation of the area under the curve, and it will just return a number, but it won't graph it for us. So we want to graph it. And again, trying to follow the logics, you'll see that we've got the left endpoints, which are all the exabytes, and the right endpoints are exabyte plus 2. In other words, the far left never gets used as a right endpoint. You've got to go over 2 because you're always taking 2 together. And the centers would be x of I plus 1. And the y left would be f of x left. And y right would be f of x right. And y center would be f of x center. Plugging in each of these values into the quadratic equation gives us 3 equations and 3 unknowns. And that gives us the ability to then solve for that, which will let us find the parabola going through those 3 points. So we don't need to worry about all of that. I've printed the code for Simpson's rule down here without the graphing in red so that you can see what's actually being added. The black code is what's new and what needs to be added to the code. So this is what we've already coded here in red. We've already put all this in, and this is producing the approximation using Simpson's rule. Now we want to add in some code. So we want to plot a figure, and we've changed code from here to the second to the last line. The rest of this simply builds out the graph of Simpson's rule. I'm not going to go into great detail, but you can see from what we're doing here that basically we're plotting a series of points, and this is going to give us the solutions. Now, it takes a lot of work in order to get the plot correct because we have to plot those parabolic tops. Maybe I should go a little slower so those of you who are not in my class can actually freeze the frame and copy down the code so that you can see what's done. So again, we're going through and we're building a coefficient matrix and a constant matrix, and we're solving for a system of equations using linear algebra. Now, I don't expect my students to understand linear algebra, and so I do not expect my students to know how to code this on their own. This is rather advanced coding. This is something that I created. Don't worry about it. If I'm not doing it very often, I forget myself what exactly it does. But basically, it's returning, graphing the parabolas. And so we have all these different commands which will enable us to solve the quadratic equation for the parabolic top. So hopefully you're able to pause the video where you need to and copy down all the lines of code, right? And then at the very end, notice that return Simpson is something that was already in there. So we're actually inserting the plotting commands inside of the Simpson's rule. Now, there is no visible output from just the command until I call it up. So there's a lot of code here. And this is what it looks like in CoCalc. You can see the indentation here. This one is not indented because it is a comment starting with 3 straight quote marks and ending with 3 straight quote marks. So it doesn't indent the second line of that. And then it will not produce any output until you actually tell it and call it up using a function, a lower limit of integration, an upper limit of integration, and an even number of subintervals. So now we're going to repeat what we did before. We're going to use the same test function as what we did previously, x cubed divided by e to the x between 0 and 8. Remember that value for the exact area under the curve is still stored under exact. It's actually not exact because it was a floating decimal point number, but it's roughly correct. And we're going to run it 3 times, one with 4 boxes. So we'll just have 2 parabolic tops, one for the first pair, one for the second pair, 4 subintervals or 8 subintervals, so 4 parabolic tops, and then 16 subintervals, so 8 parabolic tops. So we're going to call it up 3 different times for 4, 8, and 16 again. So again, we're going to say simps underscore 4 is going to be the out point of simps vector plot v, 0, 8, and 4. And then we're going to print Simpson's rule with n equal 4 is simps 4. And then we're going to call up and do the same thing for 8 and for 16. And of course, after we're done with this, we will look at the error code. So here's the first one. And what's kind of nice about the way that we drew the plot is you can see the subintervals separated by the red vertical lines. And you can see it shaded them in green. If you don't like green, you can find the G somewhere in the code, and you can change it to a B for blue, or I think there's M for magenta and some other C for cyan, which is kind of a turquoise color, whatever you like. And you can tell here also, you can see the parabolic top. So it's drawing a parabola between the first 2, and then it's drawing a different parabola between the second 2. And it's giving us the approximation down here, which is 5.99. Then we can do it again with 8. And you can see that this is a much closer approximation and got even closer than we did with the trapezoidal rule. So again, it's taking 2 pairs of boxes and it's connecting these with one parabola, and then these with a parabola, these 2 with a parabola, and these 2 with a parabola. So those aren't the same parabolas. That's actually 4 separate parabolas on the tops of each 2 pair of successive subintervals. And then on 16, it is so incredibly close to the actual curve that we can't see any white space at all. So let's go ahead and approximate the error in this approximation. And we can do the code basically the same way we did before. We'll take exact minus simps 4 or simps 8 or simps 16, and we'll print out the error and see what it looks like. So here's the code and the output from CoCalc. And we can see that this is actually more accurate than the trapezoidal rule. And the trapezoidal rule, we started off, I can't remember, 0.6 apart or something like this. This gets far more accurate more quickly. And we can see that on 16, it's much more accurate. Now, again, I want you to try this on your own. So you're going to go down here. We're going to use the same function x of sine x squared from 0 to 5. And remember that we stored the exact value in exact w. Don't forget to use np.sine for the sine function. Don't forget to use a double asterisk for the power of x squared. And don't forget to change the limits of integration to 0 to 5. Now, I hope that this explains to you how to do Python programming to approximate the area under a curve using the trapezoidal rule and the Simpson's rule. These are just two techniques that we use along with the left Riemann sum, the right Riemann sum, and the midpoint Riemann sum. And then you may ask yourself, well, which one is the most accurate? And shockingly, surprisingly, the most accurate tends to be still the midpoint rule. So if you have some function that you're trying to approximate and you want to get a relatively good approximation, my advice is to use the midpoint rule. This is the end of our discussion of numerical integration. In the next video, we will be going on and talking about improper integrals.